Hello everyone, Victor is here, your organic chemistry tutor, and today I want to look at this mechanism where we have the alkyne with a few aromatic rings on it, and we are going to treat it with water in the presence of the tazelic acid, and we are going to make this complex looking molecule on the right. And our task is to figure out the mechanism of this reaction. Well, probably the most reasonable starting point for us will be to protonate our triple bond. So I'm going to say that I have my H+ that's coming from either H3O+ or from the tazelic acid right away, and we are going to protonate our triple bond, which would give us a carbocation looking like this. Now, I had two options for my carbocation. I could have put my carbocation on carbon number 1 over here, or I could put my carbocation on carbon number 2 the way I did. The reason why I chose the one on the bottom is because it's going to be more stabilized via the resonance, where this entire part of the molecule would be potentially able to resonance stabilize that, while in the other case, the resonance stabilization could only potentially come from the aromatic ring, and that's it. Now, a carbocation is an excellent electrophile, and we don't really have any good nucleophiles in our system. We do, however, have a triple bond over here which can potentially serve as a nucleophile. While it's not necessarily a very good nucleophile, carbocations are exceptional electrophiles, which means that it doesn't really matter how bad of a nucleophile triple bond is, the carbocation will still be able to react with that without too much trouble. So that means that I can show the following curved arrow for my electron movement. Now, in this case, I have two options where I can take my carbon number 1 and I can make a bond either with this carbon number 4 over here or carbon number 5 down there. Obviously, for the reasons of stability, it would be better if we end up with a 5-membered ring rather than the 4-membered ring, which means I'm going to end up with the following carbocationic intermediate. Now, from this point, I'm probably going to be looking for another nucleophile within my system, something external, because there is nothing really else I can do within the system itself, and the only other external nucleophile that we have in this case is going to be our water molecule H2O, so we are going to do the reaction with our H2O, giving us this intermediate. Now, of course, we're not particularly happy with this intermediate because we have a positively charged oxygen, so we are going to have to deprotonate that, and for these purposes I'm going to use another equivalent of my water, or I could potentially use a conjugate base from my tazelic acid, TSO-, doesn't really matter for our purposes. Statistically speaking, it's probably most likely going to be water. So water going to come in, pull that proton off, making the following enol intermediate. And the last part that we have here is going to be the keto-enol tautomerization to bring it to a keto form. In order to do that, we are again going to be using our acid, so I'm going to show another equivalent of my H+ coming from either tazelic acid or H3O+, doesn't matter, and we are going to show that these electrons go here, these electrons go here, and we are going to be catching our proton with the very last pi bond. Remember that the entire system here is a one-conjugated system, so this whole system over here behaves like one big organism, one big molecular orbital that's going to be reacting with our H+, and the most likely position for our H+ reaction is going to be the edge of the conjugated system. That's going to give me my protonated carbonyl, which I'm going to promptly deprotonate with another equivalent of water floating around. So I'm going to show my water, show that water grabbing that proton, and that's going to give us our target molecule. And there you have it. So did I make you scratch your head with this mechanism, or did you know how to do it? Let me know in the comments below. Thank you for watching. If you have any questions or feedback, leave them in the comments below as well. I love reading your comments and engaging in conversations with you guys. You're awesome. If you learned something new today, hit that like button to help promote this video and help more students see it. Subscribe to the channel for daily organic chemistry updates, watch this video next, and I will see you tomorrow.